Welcome to the deep dive. So you've set us a really fascinating mix this time. We've got diagrams, definitions, some pretty interesting theorems, even worked examples, and it all centers around circles.
Mm-hmm. That shape we think we know so well.
Exactly. So our mission today is to really pull out the core concepts, those key insights, and build a solid understanding, fast. Go beyond just it's round.
Right, we're digging deeper than the surface, looking at the connections, the rules inside the circle. Think of it like an express lane to really appreciating circle geometry.
Okay, so let's kick us off right at the beginning. What is a circle, fundamentally?
Well, at its heart, it's a closed curve.
Right.
And the key thing is every single point on that curve, it's the exact same distance from one fixed point inside.
The center.
The center, exactly. And that fixed distance, we call that the radius.
Pretty straightforward starting point.
It is. And, another way to think about that curve, which is helpful, is as a locus.
Locus.
Yeah, imagine a point moving around, but it has to stay the same distance from that center spot. The path it traces. That is the circle. It's basically all the points that follow that one rule.
Oh. Makes it feel more active somehow.
Yeah.
And if you walk that whole path...
That total distance is the circumference, the perimeter, basically.
Yeah. Now, the materials also talk about different types of circles. Things get a bit more specific here. First up, concentric circles.
Yeah, think of like a bullseye on a dartboard. They share the exact same center point.
Ah, right.
But they have different radii, so they're different sizes nested inside each other.
Got it. And then equal circles. Or congruent.
Those are just circles with the same radius. Simple as that. Identical copies, essentially.
Okay. And then we get into circles interacting with polygons, shapes with straight sides. There's the circumscribed circle. What's that?
Okay, picture a polygon, maybe a triangle or square. Now imagine drawing a circle around it.
Outside it.
Outside it, yeah, so that the circle just touches every single corner, every vertex of the polygon. That circle center is the circumcenter. And we say the polygon is inscribed inside the circle. The diagrams you sent show this well.
Right, so the circle's kind of hugging the polygon at its point.
Exactly. Now, the flip side is the inscribed circle, or the in-circle.
So inside this time.
Inside, yeah. Picture the circle tucked inside the polygon, and now it's touching each side of the polygon, just barely grazing each side at one point.
Oh.
The center of the circle is the in-center. And here, the polygon is circumscribed about the circle. It's on the outside.
Okay, let me try and nail this down. Circumscribed circle. Circle outside, polygon inside, touching corners.
Yep.
Scribed circle. Circle inside, polygon outside, touching sides.
Oh, got it.
Cool. Okay, now let's talk lines within the circle. First up, the chord.
Simple idea. A chord is just a straight line segment that connects any 2 points on the circle's edge, the circumference.
Just draw a line edge to edge.
Pretty much.
And the diameter. We all know that one, but it's technically a chord too, isn't it?
Yeah.
That's special.
It is a chord, yes, but it's the special chord that goes right through the center of the circle.
Okay.
And here's a key thing, the diameter. It's the longest possible chord you can draw in that circle.
That makes sense, yeah. Anything else is sort of cutting a corner.
Right. It has to be shorter if it doesn't go through the middle.
Now, this is where I found it gets really interesting. The link between the center and these chords. There are some rules.
Some really neat symmetry.
First one, if you draw a line from the center and it cuts a chord exactly in half, bisects it.
As long as it's not the diameter itself.
Right, a non-diameter chord. Then that line from the center hits the chord at a right angle, perpendicular.
Always. The diagram shows it, OM cuts AB in half, so angles OMA and OMB are both 90 degrees. Guaranteed.
And the reverse is true too.
It is. If you draw a line from the center that is perpendicular to a chord, hits it at 90 degrees, then that line must cut the chord into 2 equal pieces. It bisects it.
So perpendicular implies bisected, and bisected implies perpendicular, from the center anyway.
Exactly. It's this perfect relationship.
It really feels like the center is this, like balancing point. And there's another relationship between chord lengths and distance from the center. What's the deal there?
Yeah, this one's maybe a little counterintuitive at first. The longer a chord is, the closer it actually sits to the center of the circle.
Really? Longer means closer.
Yep. And shorter chords, they're further away. Think about it. The longest chord is the diameter, which goes through the center, distance 0. Any shorter chord must be further away.
Okay, I see it now. The diagram with AB longer than CD and its distance OP being shorter than OQ makes that clear. Closer you get to the full width, the closer you are to the middle.
Precisely.
That's a neat insight. Now, another fundamental point mentioned. Only one circle can pass through 3 points if they're not in a straight line. 3 non-collinear points. Why is that important?
Well, think about it physically. If you have 3 pegs not in a row, you can rest a hoop on them in only one specific way, right?
Yeah, I guess so.
Mathematically, those 3 points uniquely lock down where the center has to be and what the radius must be. There's only one possibility. It's actually super useful in things like design or surveying.
Defining a curve from just 3 points.
Cool.
And lastly, for this foundational bit, what about chords that are the same length?
Ah, yes, this ties back to the distance thing.
Yeah.
If you have 2 chords in the same circle, or identical circles, and they're exactly the same length,
Yeah.
then they must be the same distance from the center. And of course, the other way around, if 2 chords are equidistant from the center, they have to be equal in length. It's all beautifully symmetrical.
Okay, solid foundation built. Center, radius, chords, distances. Got it. Let's move on to arcs and segments. An arc is just a piece of the edge.
Exactly, like the crust on a pizza slice, that curved part, that's an arc.
And if you draw a chord...
That chord splits the whole circumference into 2 arcs.
Right, and one's usually bigger than the other, unless it's a diameter.
Correct. The smaller one, less than a semicircle, that's the minor arc.
Like APB in the diagram.
And the bigger one, more than a semicircle, that's the major arc.
Yeah.
AQB in that same diagram.
Minor and major arc. Okay, and the segment.
The segment is the area that's trapped between the arc and the chord that made it.
Ah, the whole slice, not just the crust.
Sort of, yeah. So you have a minor segment, the area bounded by the minor arc and the chord, and a major segment bounded by the major arc and the same chord.
Okay, arcs are lengths, segments are areas. Got it.
Sure.
Now, the theorems. This feels like where the real power is. Theorem 5 looks crucial. The angle an arc makes at the center is double the angle it makes at any point on the rest of the circumference. Let's unpack that.
This is a big one, a real workhorse. So take an arc, like arc AB.
Okay.
Draw lines from A and B to the center, O. That makes an angle AOB. That's the angle at the center.
Right.
Now, pick any other point. Let's call it C, somewhere on the other part of the circle's edge.
Okay, on the major arc in this case.
Doesn't matter where, just not on the arc AB itself. Draw lines from A and B to that point C. That makes angle ACB.
The angle at the circumference.
Exactly. Theorem 5 says that angle AOB at the center is always exactly twice angle ACB at the circumference.
Always double. How does that work? The proof looked a bit involved. Constructing lines, looking at triangles.
It does use some clever geometry. It draws a line through C and the center O, and then uses the fact that triangles AOC and BOC are isosceles, because OA, OB, OC are all radii.
Okay. Equal sides mean equal base angles.
Right. And then it uses a rule about exterior angles of a triangle being equal to the sum of the 2 opposite interior angles. Putting that together step by step proves the central angle is double the inscribed angle.
So it boils down to basic triangle rules, just applied cleverly.
Pretty much. And the cool thing, as the figures show, is it works wherever you put that point C on the remaining arc. The relationship holds. Sometimes you might need to consider the reflex angle at the center, but the doubling rule is constant.
Okay, Theorem 5, central angle is double circumference angle. Got it. Now Theorem 6, angles in the same segment of a circle are equal. This feels connected.
It flows directly from Theorem 5, actually. If you have a bunch of angles all standing on the same arc, meaning their corners are on the circumference and their feet are at the ends of the same arc.
Like angle ACB and angle ADB in the diagram, both standing on arc AB.
Exactly. Since both of those angles are subtended by the same arc AB, Theorem 5 tells us that the angle at the center AOB is double each of them.
So if AOB is double ACB and AOB is also double ADB,
then ACB and ADB must be equal to each other.
Makes perfect sense. They look equal in the diagram, and now we know why. So angles looking at the same slice of the circle from the edge are always the same size.
Yep. It's a super useful shortcut for finding unknown angles.
Okay. Next, Theorem 7. The angle in a semicircle is a right angle. 90 degrees. Heard this one before.
It's a classic. And guess what? It's just a special case of Theorem 5 again.
How so?
Well, if your arc is a semicircle, meaning the chord connecting its ends is actually the diameter, say AB.
Okay, going through the center.
Then the angle that arc makes at the center, angle AOB, is just a straight line.
180 degrees.
Exactly. Now, Theorem 5 says the angle at any point C on the circumference, angle ACB, must be half of that central angle.
Half of 180 is 90.
Bingo. Any angle inscribed in a semicircle is always a right angle.
Wow, okay. It's cool how they link together like that. It's not just a random fact.
Not at all. It's all connected.
All right, let's move on to cyclic quadrilaterals. So cyclic just means all 4 corners are on the circle edge.
Yep. A quadrilateral whose vertices all lie on the circumference of a circle, those points are called concyclic points.
Okay, and Theorem 8 gives us a key property. Opposite angles of a cyclic quadrilateral are supplementary, meaning they add up to
180 degrees. Take any two angles opposite each other in that shape, add them together, you always get 180.
Why is that? Does it relate to arcs again?
It does. You can think about the arcs the opposite angles are standing on. One opposite angle subtends one arc. The other opposite angle subtends the remaining arc of the circle. Using Theorem 5 again, connecting these angles back to the angles the arcs make at the center, you can show their sum must be half of the full 360 degrees around the center.
Half of 360 is 180.
Okay. And importantly, the reverse is also true. If you find any quadrilateral where a pair of opposite angles adds up to 180.
Then it must be cyclic. You could draw a circle through all four corners.
Guaranteed. It's a test for cyclic quadrilaterals. The notes also mention angles in major segments are acute, minor segments are obtuse. That kind of fits with the visual, doesn't it?
Yeah, the bigger slice has the smaller angle, smaller slice has the bigger angle. Makes sense. Okay, one more theorem. Theorem 9. The exterior angle of a cyclic quadrilateral equals the interior opposite angle.
Right. So imagine you extend one side of the cyclic quad, say side AB, out past B to a point E.
Okay, creating an angle outside the shape?
That angle outside, angle CDE, is exactly the same size as the angle inside the quad at the diagonally opposite corner, angle ADC.
Huh, why is that?
It's quite neat. Angle CBE and the interior angle next to it, ADC, they form a straight line, right? So they add up to 180.
Right.
But we also know from Theorem 8 that the opposite interior angles, ABC and ADC, also add up to 180 because it's a cyclic quad.
So if ABC plus CBE equals 180 and ABC plus ADC equals 180.
Then CDE must equal ADC. They have to be the same.
Clever. Okay, wow. That's a lot of powerful rules we've covered. Definitions, chords, arcs, segments, these key theorems. Now let's see how they actually work with these solved examples. That's where it really clicks, I find.
Absolutely. The examples are where the theory becomes a practical tool. Let's walk through them.
Okay, example 1. We've got center O. Angle AOC at the center is 110 degrees. Find angles ADC, ABC, and OAC.
Right. So angle ADC is at the circumference, standing on the same arc AC as the central angle AOC.
So it's half of AOC. Half of 110 is 55 degrees.
Exactly. Angle ADC is 55. Now ABCD is cyclic.
So opposite angles add to 180. Angle ABC is opposite ADC.
Meaning angle ABC equals 180 minus 55.
Which is 125 degrees. Got it. And OAC. That's inside triangle AOC.
Yep. And what kind of triangle is AOC? Look at sides OA and OC.
They're both radii, so they're equal. It's an isosceles triangle.
Right, which means the base angles opposite those sides are equal. Angle OAC equals angle OCA.
And angles in a triangle add to 180. So 180 minus the known angle AOC, 1 of 10, leaves 70 degrees for the two base angles combined.
And since they're equal, each one must be half of 70.
35 degrees. So angle OAC is 35. Nice. We're using 3 different ideas there.
See, they weave together.
Okay, example 2. Triangle PQR inside a circle. PQ equals with PR, so it's isosceles. Angle PRQ is 70. Find angle QAR.
Okay, if triangle TQR is isosceles with PQPR, then angle PQR is also
70 degrees, same as PRQ.
Right, so the third angle in that triangle, QPR, must be 180 minus 70 plus 70.
180 minus 140 is 40 degrees, so angle QPR is 40. How does that help find QAR?
Look at where angles QAR and QPR are standing. Which arc do they both subtend?
They both have their feet at Q and R. They're subtending arc QR.
And their corners A and P are both on the circumference, so...
Angles in the same segment are equal. Theorem 6. Angle QAR must be the same as QPR.
Which means QAR is
40 degrees.
Cool.
Straightforward application that time. Example 3. Points A, B, C, D on the circle. Angle BAC is 67 degrees. Find the sum of angle DBC and angle DCB.
Okay, focus on angle BAC first. Which arc does it subtend?
It's standing on arc BC.
Right. Is there another angle shown that's also standing on arc BC from the circumference?
Let's see. Yes. Angle BDC is feet are B and C. Corner is D on the edge.
So angle BDC must be
equal to BAC. So BDC is also 67 degrees.
Okay. Now look at triangle DBC. You want the sum of two of its angles, DBC and DCB.
Now we just found the third angle, BDC, is 67.
And the angles in any triangle add up to
180. So angle DBC plus angle DCB must be 180 minus the third angle, 67.
Which is
113 degrees. Got it.
Combining same segment rule and triangle basics again.
Example 4 looks trickier. Parallel lines BC and DE, O is the center, angle CDE equals X. Find angle BAC in terms of X. And there are 3 methods. Wow.
Yeah, this shows the flexibility. Method 1 uses parallel lines first. Since BCDE, the alternate interior angles BCD and CDE are equal.
So angle BCD is also x.
Right. Now connect to the center. Angle BOD is double angle BCD. Theorem 5, watch the arc. So BOD equals 2x. Similarly, angle COE is double angle CDE. So COE equals 2x.
Okay, we have two angles at the center.
And DOE is a straight line, a diameter, so it's 180 degrees. Angle BOC plus angle BOC must equal 180.
So 2x plus angle BOC equals 180. Angle BOC equals 184x.
Exactly. And angle BAC is subtended by the same arc, BC.
So BAC is half of angle BOC, half of 184x.
Which simplifies to 92x.
Okay, that's one way. Method 2 uses the semicircle rule.
Yeah, it finds angle CBE first, using cyclic quad properties, then angle BCE using triangle BCE, where COE is known, then uses angle in a semicircle for CAE. It works through different steps to get the same result.
And method 3.
Uses alternate angles again, but differently than angles in the same segment to find parts of angle BAC, BAD, and DAC, and adds them up. Still gets 92x.
It's really good to see there isn't always just one path.
Definitely. Choose the one that makes most sense to you.
Example 5. AC is a diameter. AB equals BC. Angle AED equals 118. Find DEC and DAB.
Okay, AC is diameter. What does that immediately tell us about angle ABC?
Angle in a semicircle. It's 90 degrees.
Right, and also angle AEC.
Also 90 degrees, standing on the same diameter.
Okay, we know angle AED, the whole thing, is 118, and part of it, AEC, is 90.
So the other part, DEC, must be 118 minus 90, 28 degrees. First part done.
Good. Now for DAD, let's find its pieces. Angle DEC. Which arc does it subtend?
Arc DC.
And which other angle subtends arc DC?
Angle DEC, which we just found is 28 degrees.
So angle DC must also be
28 degrees, angles in the same segment. Okay, we need angle BAC now to get the whole angle DAD.
Look at triangle ABC. We know angle ABC is 90, and we were told AB equals BC.
Ah, it's an isosceles right-angled triangle. So the other two angles, BAC and DCA, must be equal and add up to 90.
Meaning each one is?
45 degrees, so BAC is 45.
Right, so angle DAB is angle DAC plus angle BAC.
That's 28 plus 45, 73 degrees.
You got it, putting the pieces together.
Example 6 is a proof. Chords AC and BD cross at 90 degrees. Angle OAB equals A, angle DBC equals B, prove AB.
Okay, start with triangle AOB. OA equals OB because they're radii.
So it's isosceles. Angle OBA must also be A.
Right, so the angle at the center, AOB, is 182A.
Okay, now connect that to the circumference. Angle ACB subtends the same arc AB.
So angle ACB is half of angle AOB, half of 182A.
Which is 90A, so angle ACB is 90A.
Now look at the small triangle where the chords intersect. Let's call the intersection point M triangle BMC.
Okay, we know angle BMC is 90 degrees given. We want angle DBC, which is B. We just found angle BCM, which is the same as ACB, is 90A.
And the angles in triangle BMC must add up to 180. So 90 plus angle DBC plus angle BCM equals 180.
90 plus B plus 90A was 180.
Simplify that. 180 plus BA equals 180.
Subtract 180 from both sides. BA equals 0, which means proof done.
That's neat. It is quite elegant.
Example 7. Cyclic quad ABCD. Exterior angle CBQ equals 48. Angle DOD equals A angle BCD B and angles 2B. AB.
Yeah.
Key property.
Yeah.
Exterior angle equals interior opposite angle.
So angle CBQ 48 must equal angle ADC inside.
Exactly. Angle ADC equals 48 degrees.
We also know opposite angles in a cyclic quad add to 180. So angle DAB plus angle BCD equals 180.
Which is a plus B equals 180.
And we're given a 2B. Substitute that in.
2B plus B was 180.
BB equals 180.
So B is degree.
Simple substitution once you apply the right theorems.
Last one, example 8. Cyclic quad ABCD. BADED, ADD, PBT equals 55, BDC equals 45, find BCD, ADB, and show AC as a diameter.
Okay, first angle BCD. It's opposite BAD in a cyclic quad.
So BCD at 180, BAD was 180, 80 equals 100 degrees. Easy start.
Now angle ADB. Look inside triangle ABD. We know BAD 80 and ABD 55.
So ADB was 180 plus 55. That's 180, 145 equals 45 degrees.
Okay. Now how do we show AC as a diameter? What's the test?
We need to show an angle subtended by AC at the circumference is 90 degrees, like angle ABC or angle ADC.
Let's try finding angle ABC. It's made of ABD, which is 55, and DBC. We need DBC.
Angle DBC. It subtends arc DC. Does anything else subtend arc DC?
Yes, angle DD. So angle DBC equals angle DC. How do we find DC?
I mean, look at triangle ADC. We know BDD is 80. We found ADB is 45. We're given BDC is 45. So the whole angle ADC is ADB plus BDC plus 45 plus 45 was 90 degrees.
Okay, angle ADC is 90.
Wait, if angle ADC is 90 degrees and it's subtended by AC.
Oh, AC must be the diameter. Angle in a semicircle is a right angle. We've proved it.
Wow, we didn't even need angle ABC. Finding angle ADC was enough. Okay, let's just double check angle ABC for completeness. Angles BAC and BDC subtend the same arc. BC is 45, so BAC is 45.
Right.
In triangle ABC, we have BAC also 45. Angle ACB subtends arc AV. Angle ADB also subtends arc AB, and ADB is 45, so angle ACB is 45.
Okay.
So in triangle ABC, angles are 45 and 45. The third angle ABC must be 180. 45 plus 45 equals 90 degrees. It works out both ways.
Perfect. Confirms AC is the diameter. A really nice example tying lots of things together.
Okay, wow, that was a fantastic journey through circles. So, wrapping this up, what's the main takeaway?
I think the big thing is that circles aren't just simple shapes. They have this incredibly rich internal logic. These theorems give us a really powerful toolkit for figuring out relationships, angles, lengths, often in ways you wouldn't expect.
Yeah, definitely. We started with the basics, the definitions, radius, chord, then saw how they connect through things like distance from the center, then the arcs and segments, and finally those really core theorems.
Especially that central angle theorem, Theorem 5. It felt like it kept popping up as the reason behind other rules, like the angle in a semicircle or angles in the same segment.
It really did seem foundational, and the cyclic quadrilateral rules are so specific and useful too. Seeing them used in the examples really drove home how practical this geometry is.
Exactly. It's not just abstract rules. It's a way of solving problems and seeing connections.
So now that we've seen, how these seemingly simple circle parts are all linked in these quite deep ways, it makes you wonder, doesn't it? What other shapes that we think are basic, maybe like spheres or other polygons, might have these hidden, elegant relationships waiting to be uncovered?
That's a great question to ponder. This dive into circles really just scratches the surface of the beauty and structure within geometry. There's always more to explore.
Well, thanks for taking this deep dive into circles with us. Until next time.